Hello everyone, and welcome to the Kinetic Energy Pre-Lab. So up to this point, we've developed a couple of math models for our energy storage mechanisms. We started by building a math model for the elastic potential energy stored in a stretched or compressed ideal spring, 1/2 kx squared. And then today we built a math model for the gravitational potential energy stored in the gravitational field between an object and the Earth, mgy. So today what we're going to work on is the kinetic energy math model. Kinetic energy is, of course, the energy of motion, the ability to produce change something has because it's moving. After all, something that's moving is already producing change. It's changing position. So, we need to start out here by deciding what variables might affect how much kinetic energy was stored in a moving object. Right, so the first one, let's consider if I threw a ball at you, and if I wanted to do some more damage, right? If I wanted to produce more change, what could I do with that ball? Well, I could throw it faster, for example. Right, so perhaps the speed has something to do with the kinetic energy. After all, something that's moving faster is changing position more quickly. But I could do something else to that ball. If it started out as a tennis ball, maybe I could change it into a softball, or a shot put, or a bowling ball. And as long as I could throw those at you at the same speed, wouldn't they each produce a different amount of change? Sure, because what's different about them? Their mass. So we would expect that when we eventually build a math model for kinetic energy, it'll have something to do with the speed of the object and something to do with the object's mass. Hence, the purpose of this lab is to create graphical and mathematical representations of the relationship between the kinetic energy, the speed, and the mass of a superconducting levitating puck moving down a ramp. Yes, indeedy, we are going to do a little Pivot Interactive here, and that's what's in the Pivot Interactive, a superconducting levitating puck. They have a real nice movie about it, but let me show you just a little video here of what it looks like inside of Pivot Interactive. So this is the video inside of the Kinetic Energy Lab Pivot Interactive, and it's kind of cool. You'll notice here we've got this maglev little disc over here, which can move with basically no friction. So let me show you here what it looks like. Very cool, if you notice. It moves on this little curved part of the track, and then there's the horizontal part of the track. So kind of two different kinds of motions going on here that we can look at from a motion perspective, or, in this case, an energy perspective. Over here, remember, you can change some things. Like here, you can change different heights. All right, so do that, click load. All right, and so now you can see it's being released at a different height. Right. Up here, we can turn on all sorts of tools. This is the Stopwatch tool. If you click that, that'll restart it from 0. Very handy. Tells you how many frames. Vertical ruler, which you can move around wherever you want. Horizontal line will come into play. This will put dots on here that you can then move around the screen. You can either grab them and drag them, or you can use your up and down arrow keys and things. Right, to put these anywhere you want, and then a horizontal one, a horizontal ruler. So all these things are up here. Now there's a lot of instructions about this, right? But this is how we are going to look at the relationship between the kinetic energy and the speed. And in your case, you don't have to worry about any frictional effects because of this cool little thing. And by the way, there's a short little video that even explains this. And how it's set up and everything, which is kind of cool. So this is the Pivot Interactive for the Kinetic Energy Lab. So how then are we going to employ energy with this? Well, let's take a look at two different places, right? Right when it's released up here, and then when it gets down to the horizontal part. So at the highest point up here, right? It's going to start from a height that is greater than 0. Remember, y is vertical position. So our yi, our initial height, is greater than 0, but it's going to start from rest. We let it go and it moves, and when it gets down here, right, now it has a height we're going to call 0, so we'll call this final height 0. Why not, right? We should measure it from there, hint, hint, when you get into your Pivot Interactive. But it will have a speed greater than 0. How will you measure the speed? Well, it's a distance over time thing, but there are some instructions in the Pivot Interactive. Okay? So this is our initial, and this is our final. Okay? So if we're going to look at this from an energy perspective, we need to define the system. So let's use the puck, let's use the track, and let's use the Earth. And if we put those in there, is that an isolated system? Well, let's consider the forces that are acting on the puck. Right? There's a force of gravity. That's between the puck and the Earth, so that's in there. There's a magnetic force, right, as this is a superconducting levitating puck, and that's between the puck and the track, so that force is internal, and no friction, so that's pretty much it. Right? So all of the forces are internal, therefore the system is isolated. And when a system is isolated, the total amount of energy doesn't change, it is conserved. So we can compare the energy at the highest point where it's released to the energy that it has when it's on the horizontal part of the track. So let's take a look at that from a pie chart perspective. First of all, notice I've made the pies the same size because after all, the energy is conserved. So initially, what is this pie filled with? What is the energy stored as? Well, there's no springs, right? It's not moving, but it is off the ground and is going to fall. So that means this pie is all filled with gravitational potential energy. And remember, we now know how to calculate that gravitational potential energy, so long as we know the mass of the puck, which is given to you, gravitational field strength, which we know in this room is our old friend 9.8 newtons per kilogram, and the height, which we will show you in the pivot, you can measure. Finally, when it's down here, well, there's no more EG left, right, because we're calling that height 0. No friction, so no dissipated energy. No springs. So all that's left, it's all kinetic. So if I want to know how much kinetic energy the puck has at the bottom of the ramp, all I really need to do is calculate the amount of gravitational potential it starts with, and those two things will be equal to one another. There's lots of little calculations to make in this lab. So we're not actually going to measure directly how much kinetic energy. We're going to infer it by using this very cool conservation of energy machine with the superconducting levitating puck moving down the ramp, because we can take the initial EGI, which we can calculate, and compare it to the final EK, final kinetic energy, which will have the same number of joules, same amount of energy, right? So we can actually figure out how much EK there is here. And we can compare that to how fast it's going down here, as long as we don't change the mass. Right? We're going to use, although there are two different masses in the videos, we're only going to use mass 1. Okay, I don't want you to change the mass because it's hard to keep the speed constant. So we're just going to do 1/2 of the lab. We will be able to figure out where the mass figures in during the post lab. So do this whole pivot, take the data in the pivot, follow the instructions, and then you can finish your lab sheet after a whole bunch of work also with graphical analysis. So I hope you enjoy doing this rather cool kinetic energy lab using Pivot Interactives.